Well, what we learned so far? We learned that in our class, we're dealing with two different types of variables. First, we discussed discrete or countable variable, and then we start talking about continuous variable. So we denote these variables by x. To visualize probability distribution for discrete random variable, we use a histogram. In this histogram, on the horizontal axis, we have our x, and on vertical axis, we have the relative frequency distribution, relative frequency, and then we have some bars representing the relative frequency for each of these variables. Since it's discrete, we have finite numbers of bars. Remember that we talked about continuous random variable, and to visualize this, we're going to use a histogram, but since these bars are going to be very small, we're just looking at the general behavior of our graph. So we have our x on the horizontal axis, and here, instead of having relative frequency and forming relative frequency distribution, we use probability of random variable x. Again, recall that these bars are going to be very small, tiny slant bars. And by graphing these, we can follow the behavior of probability distribution P of x here. Well, we learned that if we have random variable x for a continuous random variable, we can convert that into standardized score or z-score. Z-score is equal to x minus the mean divided by standard deviation, or x minus mu divided by sigma. Mu, the mean of the population, and sigma, the standard deviation of population. We also learned that for a normal or bell-shaped graph distribution, the graph is like this. Well, here we have our horizontal axis. We have our x values. And on top of it, we have a normal distribution. So I'm using the same color as I used for my bars and these little tiny bars here to show the distribution. So normal distribution. These are all your bars below the graph. They're representing the probability distribution for random variable x. Remember that the midpoint, the middle point, the center, the typical value in a normal distribution representing the mean. If you're working with population, it's going to be mu. If you're working with sample, it's going to be X bar. Then we started dividing up this line using sigma. Mu plus 1 standard deviation, mu minus 1 standard deviation. Then we continue this process. Mu plus 2 standard deviation, mu minus 2 standard deviation. So this number here is mu plus 2 standard deviation. This number here is mu minus 2 standard deviation. And then here we have mu plus 3 standard deviation. And finally, on far left, we have mu minus 3 standard deviation. Remember that you can take each X value on the horizontal axis and convert that into Z. Well, if you convert that into Z, you're going to get the same horizontal axis, the same normal distribution, with the same bars. On the horizontal line, instead of having X, we're going to have Z. Well, okay, now that we are changing X into Z, what is the typical value for Z score? Is it going to be the same as X? Of course not. In the middle, we have X equals to mu. So if I plug in mu for X, I get mu minus mu, which is 0, divided by standard deviation. 0 divided by standard deviation is going to be 0. So now our typical value, the center, the middle point, is going to be 0. Mu for X is now 0 for Z. Well, okay, my mu is equal to 0. So now your X is equal to sigma. Sigma minus 0 divided by sigma is equal to 1. So the next number on the right-hand side of 0 is 1, and the number on the left-hand side of 0 is minus 1. So see the difference between these? When you're working with X, the middle number is mu, the mean of the population. When you're working with Z scores, the typical value, the center, is nothing but 0. Mu shifted to 0. Mu plus sigma is now 1. Mu minus sigma is now -1. Well, what about the next number? Mu plus 2 standard deviation is 2. Mu minus 2 standard deviation is -2. Okay, what about mu plus 3 standard deviations? It's going to be 3, and mu minus 3 standard deviations is going to be -3. So as a statistician, sometimes you use your original data, X values. Some other times you have to convert everything into Z. In either cases, you're going to use your calculator to calculate these probabilities. So let us officially talk about a normal distribution. Next steps, normal distributions. In previous lessons, we discussed continuous, random variables and their probability distributions. The values of a continuous random variable cannot be listed in order. This happens because for any given value, there is no next value. There is no next height after 6 feet tall. So again, recall that we talked about variables, discrete, like the numbers of students in this class. We can count them, we can put them in order, and continuous random variables. We cannot count the continuous random variables like height, weight, area, volume. We have seen that some distributions of probabilities for continuous variables are shaped like bell-shaped or symmetric with a high, middle, and low ends. What's the graph like? The graph is like a bell, nice and symmetric. Many bell-shaped probability distributions are called normal, like shoe sizes, height, weight. So normal, bell-shaped, symmetric. Note that again, when we have a normal distribution, on the horizontal axis, you have your x, and then below the graph, you have your small bars. Since they are very, very small, they are all adjacent to each other, there is no gap in between them. We just shape the whole graph instead of using these little bars here. So, but again, note that these are all frequencies for these x values. You don't see these bars anymore because these are very small. But what is below the graph, all are frequencies, relative frequencies or probabilities for each of these x values. When you have a discrete random variable, you have these bars representing your probability distribution. But for a continuous random variable, these bars are getting very small. So the graph behaves like this. For a discrete random variable, you might say, hey, I'm going to connect these together and form this graph. Yes, as you can see, if we ignore these small outsiders, we have a normal shape or bell graph, symmetric with respect to the mean. But in general, when you're dealing with a continuous random variable like x, just say, hey, Let us ignore this type of bars and just deal with a normal distribution bell-shaped graph. So this is for discrete. This is for continuous. Again, remember that the area below the graph is 1 or 100%. This is the area. This area is 100% or 1. Okay, when we say that the bell-shaped probability distributions are normal, we don't mean in most cases that they are perfectly normal. But many of these distributions are approximately normal. Soon, we will give you some rules to help you determine whether a population is approximately normal or not. For example, heights of randomly selected men have a distribution that is approximately normal. The mean of this population is mu equals to 69. So mu, the typical value, the average, the mean in the middle of the horizontal line with frequency, which is top here. This mean is 69. This mean on the horizontal axis is 69. So if I say, hey, where is the mean? You don't say, hey, mean is here. It's wrong. Mean is on the horizontal axis. So they calculated the standard deviation and after calculation, the standard deviation is 3. Well, the probability distribution has probability curve, which is normal. The area below the curve is 100% or 1. It means that if we add all of these small probabilities or relative frequencies, the sum is 100% or 1. Recall the example that we did in class for the number of residents in New York City. We added those probabilities together and then it was equal to 100% or 1. It's true for any probability distribution. Well, the normal distribution always have the following characteristics or properties. The mean and median are equal to each other. Half of all values are below the mean and the other half are above the mean. The normal curve is bell-shaped and symmetric with respect to the mean. And the area under the normal curve is equal to 1 or 100%. Okay, perfect. Next page. Normal curves extend endlessly in both directions, but they're very close to 0. So the limit is getting closer and closer to 0, but they don't touch the horizontal line. On the horizontal line, you have your x values, x equals to mean, x equals to mean plus 1 standard deviation, x can take on values in between, and so on. Note that For values more than or around 4 standard deviations above or below the mean, we say that, hey, the curve almost touches x-axis, almost touches. It's never crossing these two lines. Well, the normal curve changes its curvature. Curvature is upside. Curvature is downward. Curvature goes up again. So the normal curve changes its curvature from upward to downward and then upward at 1 standard deviation below and above the mean. So these points are called inflection points. So inflection points are the points where the curve changes its curvature. It's going up, upward curvature. Then it's going down, downward curvature. Then again, up. This is the behavior of normal curve, normal distribution. And these 2 points are called inflection points. They happen at x equals to mu minus sigma, x equals to mu plus sigma. So if you have a question about inflections, you say that, hey, we know inflection points, they happen at mu minus sigma and mu plus sigma. At these 2 points, the curvature of the graph changes. Very well. So a normal distribution is determined by its mean and standard deviation. For example, one normal distribution might have a mean of 23 with standard deviation of 1. Another normal distribution could have a mean of 15 and a standard deviation of 1.5. So each distribution is related to a random variable. That random variable might count the height. That random variable might count the shoe sizes. That random variable might count the weight, and so on. Each of these result in different frequencies, and those frequencies result in different distributions. So you're going to see different types of graphs for normal distribution. Okay. Try these. Match the following graphs of normal distribution with the appropriate means and standard deviation given in the question below. Okay, perfect. We have something to work on. Well, what do we have here? We have graph A, graph B, C, and D. We have these distributions with mean 15, standard deviation 4, mean 15, standard deviation 1, mean 13, standard deviation 2, mean 17, standard deviation 2. Okay, well, remember standard deviation. Standard deviation was a measure of variability. Standard deviation, variability. When our standard deviation is a small number, it means that we don't have that much of variability. It means that the graph is not that scattered. The graph is centered around its typical value. So you should think that, well, between mean 15 and mean 15, there is no difference in these two numbers. Their mean are both 15. Okay. The mean of the first graph is 15. Okay, here we go. The mean of graph B is also 15. Which one has more variability? Which one has the higher standard deviation? You don't see that much of variability in this graph, but the variability in this graph is high. So this has more variability. So between 1 and 4, 4 showing that you have higher variability. So 4 matches to B. As you can see, for graph A, the mean is 15, and you don't see that much of variability here. Less variability. A. Very well. Now think about question 5. The mean is 13. Okay, I see the mean equals to 13 here. So it means that the answer is C. And finally, we're left with the last normal distribution with mean equals to 17. So just right here. So this is my D. Next steps, the empirical rule. All populations that are approximately normal have similar distributions with respect to their mean and standard deviation. So again, all populations that are approximately normal, they have similar distributions. So we can come up with a general rule for them. For instance, in approximately normal populations, remember that we rarely have perfectly normal distributions. About 68% of values lie within one standard deviations of the mean. So 68% of values lie within one standard deviation up and below the mean. About 95% of values, so 68, one standard deviation, 95% of values lie within two standard deviations from the mean. And finally, 99.7% of values lie within 3 standard deviations of the mean. These facts are based on empirical evidence. They are collectively known as the empirical rule. So before doing any calculation using calculator, we're going to just talk about empirical rule a little bit. How do we use empirical rule to do the calculations without calculator? But eventually, to get the precise answer, we're going to use technology. The normal curve models or represents the empirical rule very well. The image below is a normal curve with the mean mu in the center. So this is your center. Here your x is equal to the mean. Again, on the horizontal axis, you have your x values, and these are all representing those little bars, the relative frequencies or probabilities. Okay, 68% of the data lie in one standard deviation from the mean. One standard deviation below, one standard deviation above the mean. 68%. Then 95% of the data lie below and above of the mean with 2 standard deviations. 68%, 1 standard deviation, 95%, 2 standard deviations, and finally 99.7 within 3 standard deviations. This is our last one, 99.7%. So in general, we can summarize these 3 graphs, 68%, 95%, and 99.7% here. The empirical rule, 68, 95, 99.7% rule in any normal distribution. So if you have any normal distribution, about 68% of the values lie within 1 standard deviation of the mean here. 95% lie within 2 standard deviations of the mean. Cover all of these data with frequencies, with probabilities, relative frequencies in 2 standard deviations, and finally 99.7% lie within 3 standard deviations of the mean. Covers almost everything. Okay, let's go over some examples. See these in action. The empirical rule tells us that only about 5% of values are more than 2 standard deviations from the mean. Because of this, we say that values that are more than 2 standard deviations from the mean are unusual. So this is important. Values that are more than 2 standard deviations from the mean are called unusual values. If they are more than 3 standard deviations, we call them highly unusual. So values that are more than 3 standard deviations from the mean are called highly unusual. Note that unusual and highly unusual are near the tail of your graph. Next steps. In this lesson, we learned that many populations are approximately normal in their distribution. We have used the z-score as a tool that led us to compare values from different populations. Statisticians use the z-score only for comparing values from normal populations. Let's take a look at question 8. Adult male heights are approximately normal in their distribution. They calculated the mean, it is 69, and standard deviation is also calculated to be 3. So let's highlight these two, 69 as the mean and standard deviation as 3. And we know that it's a normal distribution, approximately normal. The image below represents this distribution. The vertical lines are 1 standard deviation apart. Label the adult male heights corresponding to each vertical line below the horizontal axis. Well, okay, we know that in the middle, X is mean, 69. Standard deviation is 3. So here you have 69 plus 3, which is 72. 69 minus 3, which is 66. 72 plus 3, 75. 66 minus 3, 63. 75 plus 3, 78. And 63 minus 3, which is 60. Okay, well, remember the area under the probability curve, which is 100%. This whole area, if you add all of these relative frequencies together, it is 100% or 1. The area under the normal curve above is divided into 8 regions. 1, 2, 3, 4, 5, 6, 7, and 8. The width of each region, except the far right, except for these two here, is 1 standard deviation. In this case, our standard deviation is 3. The far right and far left regions extend endlessly, these two parts. Use the empirical rule again to find the area of each region. Now write the area for each region on the normal distribution. Okay, let us take a look at our empirical rule graph. We know that our graph says, well, 68% of the data are in between 1 standard deviation away from the mean. It means that this area here is 68%. So half of 68% is here, the other half is here. So 34%, 34%. 34%, 34, If you add these together, it is equal to 68%. 68% divided by 2 is 34%. 34% of the male heights is in between 69 to 72. That's the meaning of that. 34% of the population height, male heights, is in between 66 to 69. You can think about these as, for example, midterm score. Suppose the average midterm score is 69 with standard deviation 3. And since scores are normally distributed, I can use empirical rule and say, hey, 34% of my class got score between 69 to 72. 37% of my class got score 66 to 69. They can continue this process. Well, okay. We also know that 95% of the data are in 2 standard deviations away from the mean. I already know that 68% is in the middle here. So 95% minus 68%, 27%. 27% is divided up into 2 pieces here and here. So 27% divided by 2. 13.5%. So 13.5%, 13.5%. Again, in this example, it's about adult male heights. So we said that, hey, 13.5% of all adult male heights are in between 72 to 75. Or when you think about scores, midterm scores, I can say, hey, 13.5% of my class got score 72 to 75. 13.5% of my class got score 63 to 66. And we can continue this process. Now, for the rest of these little areas, you're going to have, okay, I'm going to write this here for you. 2.35%, 2.35%. Again, the same logic. Here you have 99.7% in 3 standard deviations. You already know that, hey, 95% is located here. So you have 99.7% minus 95%, which is 4.7%. You divide 4.7% by 2. You get 2.35% to the left and to the right. And finally, if you think about 100%, 100% minus 99.7% divided by 2, we get, let's see, 0.0015 and 0.0015 of the area. Again, the interpretation is 34% of adult male heights are in between 69 to 62. 34% is in between 66 to 69, and the rest of these interpretations.